Hello guys, and welcome to another video. So in this video we'll be looking at answering a past paper question. This one comes from last year's June exam. So let's read our statement. They are saying here that we have a 20 kg box which is initially addressed, and this part that says the object is initially addressed tells us about the initial velocity, right? And that means our initial velocity is going to be 0, and it's on a rough horizontal surface. Rough horizontal surface means there's friction. The box is pulled to the right by a constant force of 100 newtons. So we have that force there, and it is parallel to the surface. If this force is parallel to the surface, we must think of what our theta might be there, and it's definitely going to be 0. The box is moved a horizontal distance of 4 meters and experiences a frictional force of 65 newtons. So we have two forces that are acting on this object, and to make my life easy, I'm gonna add this other force. I know I have this force of 100 newtons. This is my force applied, capital letter F, and I have this other force of 65 newtons. That force is going to be my force of friction, right, as stated there. And then this is my displacement. My displacement is supposed to be delta x. Okay, I'm writing all of this information down so that when I answer my questions, life is not difficult. And then 6.1 says define the term non-conservative force. So if we define non-conservative force, we will say it is this. So we'll say that a non-conservative force is a force for which the work done in moving an object is dependent on the path taken. And this object, guys, is being moved from one point to another. Okay, so you can add that on your definition. You can say it is a force for which the work done in moving an object from one point to another is dependent on the path taken, or you can write it the way I have here. So please write this definition down. Then we go to 6.2. 6.2 says we have to name the non-conservative force acting on the 20 kg box. We have to firstly remember, guys, the types of non-conservative forces that we have. Okay, we have the force of friction, we have force applied, we have tension, and we also have air resistance. This is based on the previous video whereby we were discussing the theory around this topic. We also have air resistance. Okay, I won't write the whole way there. So here they are saying name the non-conservative force or forces acting on this object, and based on the types of non-conservative forces we have, we can see that here there definitely isn't any tension here. We don't have tension, we don't have air resistance, but we know that we have this constant force, which is the force applied. We also have this 65 newtons force, which is our force of friction. So if we answer this question, then we will say that the forces that we have are the force of friction and the force applied. Okay, so guys, those are going to be our two forces, the force of friction and the force applied. Then we go to 6.3. It says using energy principles only, calculate the speed of the box at point Z, this point here. So we know that our object is at rest at point Y. So at this point, our object is at rest, and if it's at rest, it means that at point Y, the initial velocity is equal to 0 meters per second, and that means at point Z, we should be having our final velocity, to our final speed. Okay, so that's what we are told, that the initial speed or velocity is 0. The final speed is what we are looking for, or final velocity. And for us to do that, guys, the formula that we are going to use is this one. We will use the work energy theorem, And the work energy theorem is W net is equal to change in kinetic energy, right? That's the formula we are going to use. And you will realize that for us to use this formula, we need to know what work net is. This one is our change in kinetic energy. So if I expand this formula, I know that change in kinetic energy is half mv squared final minus half mv squared initial, right? That's what I know. But what I'm gonna do first to maybe make my life easy is to start by finding my F net. Remember I said there are various ways to find work net. We said you can either find work net by looking for the sum of all the forces that are acting on this object, or you can look for your F net, or you can find the individual forces, the individual works done by the forces. We can find the work done by the applied force and then afterwards find the work done by the force of friction. But I'm gonna do this by finding firstly my F net, and that F net I will use to find W net. So F net is when I have all the forces that are acting on the object, and in this case I have the force applied plus the force of friction. Those are the two forces I have acting on the object, and my force applied is 100, and then I have my force of friction, which is going to be negative since it's acting in the opposite direction, right? So it's going to be 100 minus 65. And when I say 100 minus 65, the answer I get is 35 newtons. But I'm not looking for F net, but I'm using F net so that I can find W net. So for me to find W net, I will then substitute and say W net is equal to F net delta X cos theta. And my F net is this 35, which I just got. My delta X is this 4, okay? And I have my cos. What is going to be my theta, guys? My theta in this case is going to be 0 degrees, because we see that our F net is positive. That means it's moving in the direction of motion, and that means our object is moving in the same direction as the displacement. Thus our theta has to be 0. So now when I calculate my W net, this is what I get as my answer. So W net, guys, is going to be 140 joules. Once I have this, I'm now going to substitute into this formula. I now know what W net is, and it's 140, right? You can just pause or rewind, guys, to write some of this information. I'm taking shortcuts here. So what I'm going to do is to substitute into this formula, right? I know what my W net is. My W net is 140 is equal to half m. What is my mass? It's 20 kg. Do I know my final velocity, guys? No, I do not. In fact, the final velocity is what I'm looking for. So here I will have half 20 vf squared minus my initial velocity, but my initial velocity is actually going to be 0, right? Or rather my initial kinetic energy there, so it's going to be 0. So here I have 20 multiplied by 0 squared, so all of this is going to be 0, and that means I will have 140 is equal to half 20 is what? It's going to be 10 vf squared, and then from here I'm gonna divide by the coefficient of Vf, which is 10 on both sides, and then because I want to get rid of the square and remain with Vf, I will square root both sides. And if I square root both sides, what am I going to get as my Vf? Therefore Vf is equal to the square root of 140 divided by 10, which is 3.74 meters per second. So this is my speed, and this speed of mine, guys, is a scalar, so I don't have to put direction there. So this is the answer that you are supposed to have for 6.3. Let's look at 6.4. 6.4 says calculate the average power dissipated by the 10 newtons force between point Y and point Z. Okay. Alright, so guys, for this one, we can use various ways to solve it. Okay. The first way is to say, okay, since we are looking for the average power, we can use the formula P average is equal to our constant force multiplied by the average velocity, right? V average. Okay, and you have to keep in mind that we are looking for this, and we do have our force in this case, right? And the force that we are looking at is this one here. It is this 100 Newton force, so we can substitute it there, 100 newtons. And for our average velocity, we will find it this way. We will use one of the equations of motion. Let me just go to, okay, here guys, we will not necessarily use the equation of motion, but we will have okay, maybe let me just start here first before I proceed. So we will have this F, and then we'll multiply this force of or this applied force with what? With our final velocity. I'm substituting here our final velocity minus initial velocity, and they will be divided by 2. So this is our average velocity. Since we have two velocities here, we divide by 2. That's our average there. Okay, that's our average. Actually, it should be added, not subtracted, right? Because if we are looking for an average of something, we normally add the total, and then we add everything that we have and divide by the total of those things. Okay, so when we proceed, this will be our force, and that's 100, this 100 newtons, and our final velocity, we found it to be what? 3,74 plus our initial velocity in this case was 0, and we divide all of this by 2. And when we go to the calculator, we say 100 multiplied by, it's more like I'm seeing 3,74 divided by 2, and the answer I get is 187 watts. So this is my average power, but I can use another method. That method is where I can make use of my what you might call the equations of motion. So if we are going to use the equations of motion, guys, the first step is to find our acceleration, because we do not have the acceleration. So we'll use F net is equal to ma, and our F net is the sum of all the forces. And if you recall, but we can just quickly find it here, F net was equal to 100 minus 65, and this gave us a value of 35. So our F net is 35 is equal to, our m is the mass of this object, which is 20 multiplied by a. So we divide by 20 on both sides to get our acceleration. And if we divide by 20, say 35 divided by 20, 35 divided by 20, the answer we get for our acceleration is 1,75 meters per second. Once we have this, guys, we can now find our time. So the formula we'll be using to find our power is P is equal to W over change in time. So we want to use a formula that has power, has power, work, and change in time. Okay, So let's just quickly check which formula to work with. Okay, the formula we can use is this one, guys. We can use the formula Vf is equal to Vi plus A delta T. Our Vf is 3,74 is equal to our Vi is 0 plus our acceleration is 1,75 and our time is what we are looking for. So here it means we should simply divide by 1,75. I hope you understand the math there. And therefore delta T will be equal to what? So if I say 3,74 divided by 1,75, the answer I get is 2,14 seconds. So this is the time I'm having. So I'm going to use that time to find my power, the average power. I'm going to use the time. I'm just going to keep it there. But we have to remember that power is equal to W over delta T. So if we substitute, we are going to look at the work done by this object. And the work done by this object is produced by this 100 Newton force, right? So we will see 100 multiplied by our displacement of 4 meters cos 0 degrees divided by our time, change in time, which is 2,14, and our answer will be what? Let's see, we will have 100 multiplied by 4 cos theta, which is 400, right? Just confirming with the calculator. Cos theta divided by 2,14, and the answer we get is 186,92 watts, which is equivalent to 187 that we got when you used another method. So that's how you deal with 6.4. Okay, let's look at 6.5. So 6.5 says the box is now pulled upwards by 100 Newton force on the original surface, which is now inclined at an angle as shown in the diagram below. So this is our object now being pulled at an angle, and then they say for 6.5.1, for 6.5.1 they are saying to us, draw a labeled free body diagram showing all the conservative forces acting on the 20 kg box. So guys, if we remember what the conservative forces are, let's start with the definition. A conservative force is a force for which the work done on the object is independent on the path taken. That is the definition of a conservative force. And the examples of conservative forces are what? Are your gravitational force, your electrostatic force, and your elastic force. So in this case, which force happens to be conservative? It is definitely going to be the force of gravity. So if we draw our free body diagram, it will be like this, and we will have our force of gravity there. So this is how the free body diagram is going to be like. I know here we have 2 marks, but yeah, the one non-conservative force we have is force of gravity, nothing else. So the 2 marks there doesn't really say you have to have more than 2 forces. Okay, then we have 6.5.2. they are saying there, will the box still have the same speed after 4 meters as in question 6.3? Write only yes or no. Give a reason for the answer. What do you think the answer is, guys? I'm gonna say the answer is no, because our object is moving from the ground, right? When it's moving from the ground, that means our object will have kinetic energy, right? And it will not have any potential energy. However, as the box moves upwards and it has moved for a displacement of 4 meters, it will reach this point here. And when it reaches this point here, it means our kinetic energy is going to decrease, right? And if our kinetic energy decreases, that means that we will have negative work done, as the object will no longer be moving, right? So that means the answer will be no, and our reason will be due to the fact that negative work is being done, right? Which then makes the object to lose kinetic energy. Hence, the object will not be having the same speed. Instead, it will have a lower speed. That's how we are gonna answer this. Okay, I don't want to write it down, guys. You can just rewind and replay what I'm saying. But what I'm saying is that as the object moves up, it will be losing kinetic energy, and that means negative work will be done on the object. Hence, the object will not have the same speed. Its speed will actually become lesser, because we know that eventually the object will come to a stop as it gains potential energy. It will end up not having any kinetic energy. So that's how you answer this question, guys. I hope you enjoyed the video. If you didn't understand anything, just play back the video, guys. Go back, pause, write everything down that you need, and just enjoy physical sciences. I'll see you on the next video, guys, and please don't forget to like, share, and subscribe. See you on the next one. Bye bye.